In this lesson, we will examine hydrogenic systems. A hydrogenic system, also known as a hydrogen-like system, is a two-particle system that consists of one nucleus and one electron. An obvious example is a neutral hydrogen atom. Another example is a helium ion with a charge of +1. Recall that a neutral helium atom has 2 electrons. So a helium ion with a +1 charge has only 1 electron. Since the nucleus is much more massive than an electron, the total mass of a hydrogenic system is essentially that of the nucleus. Therefore, the translational energy of the entire atom is essentially due to the motion of the nucleus. Another consequence of the nucleus being much more massive than an electron is that the reduced mass is essentially that of the electron. This means that the kinetic energy due to the relative motion is essentially thought of as due to the motion of the electron in a coordinate system where the origin is set at the nucleus. Recall that for a two-particle system, the Hamiltonian is separable if we use center of mass and relative coordinates. This allows us to split the 6-dimensional Schrödinger equation into two 3-dimensional differential equations. The differential equation that depends on the center of mass is essentially a particle-in-a-box problem, with eigenvalues equal to the allowed translational energies. Because the nucleus is much more massive than the electron, the differential equation that depends on the relative coordinates essentially describes only the electron. Typically, we are only referring to this differential equation when we write h hat psi equals E times psi for a hydrogenic system, and we call this the electronic Schrödinger equation. H hat is called the electronic Hamiltonian, and it's the sum of the relative kinetic energy operator and the potential energy operator. The eigenfunctions are called the electronic wave functions. The eigenvalues are called the electronic energies. The potential energy due to Coulombic attraction between the electron and the nucleus is inversely proportional to the distance between them. In the formula given here, 1/4 pi epsilon naught is the Coulomb's law constant. E is the fundamental charge, 1.602, times 10 to the -19 coulombs. Negative E is the charge of an electron. Ze is the charge of the nucleus, with Z being the number of protons in the nucleus. In the plot shown here, the potential energy function is shown as a solid curve. Note the potential energy is negative and approaches 0 as the distance approaches infinity. Remember that there is no absolute scale for potential energy, so this limit is arbitrary. Infinite separation of particles is typically defined as the 0 reference point for potential energy. This means that when the total electronic energy is greater than 0, solving the electronic Schrödinger equation gives us continuum states. But when the total electronic energy is less than 0, we get bound states. The energy is quantized and the electron won't be able to escape from the nucleus. The dashed lines on the chart shows the lowest allowed energy levels. For the ground state, labeled here as E1, the electron is classically forbidden from going beyond this distance away from the nucleus. For the first excited state, labeled here as E2, the electron is classically forbidden from going beyond this distance away from the nucleus. Of course, as we have seen in earlier lessons, we expect quantum mechanics to predict a finite but very small probability of the electron tunneling into the classically forbidden region. As mentioned earlier, when the electronic energy is positive, solving the Schrödinger equation gives us continuum states. For the rest of this lesson, we will focus on the bound states, the solutions we get when the electronic energy is negative. Because the potential energy depends only on r, the distance from the origin, the electronic Schrödinger equation is an example of a central force problem. The solution to central force problems is best expressed in terms of spherical polar coordinates, r, theta, and phi. This is because the wave functions can be written as a function of r times a function of theta and phi. The functions of theta and phi are the spherical harmonics for any central force problem. These are the same spherical harmonic functions we encountered when we studied the particle on a sphere problem. However, the functions of r, called the radial wave functions, depend on how the potential energy depends on r. For hydrogenic systems, solving the Schrödinger equation yields 3 quantum numbers, n, l, and m. The quantum number n is called the principal quantum number and must be a positive integer. The quantum number l must be a non-negative integer less than n. and quantum number m, often also called m sub L, is restricted to integer values from negative L to positive L. Note that there is an additional restriction on quantum number L for hydrogenic systems. It must be less than quantum number n. Let's look at a few simple examples to familiarize ourselves with the quantum numbers. Which of the following is an allowed value for the quantum number n? Pause the video, then resume playing to check your answer. Let's see. The rule is that the principal quantum number must be a positive integer. That rules out choices A, B, and D. Choice A, 0, is not a positive integer. Choice B, 0.5, is not an integer. And choice D, -3, is obviously not a positive integer. The correct answer is C. 2 is a positive integer. Here's another example. Which of the following is an allowed value for quantum number L if the principal quantum number n is equal to 2? Pause the video to think about it, then resume to check your answer. The rule is that quantum number L must be a non-negative integer less than n. The correct answer is C, 0. For n equals 2, the allowed values of L are 0 and 1. Let's do one more example. How many allowed values are there for quantum number m if L is equal to 2? Pause the video to think about it, then resume to check your answer. The rule is that for a given L, the allowed values for quantum number m are all the integers from negative L to positive L. So, for L equals 2, the allowed values are -2, -1, 0, 1, and 2. The answer is D. There are 5 allowed m values for L equals 2. In general, for a given L, the number of allowed m values is 2L plus 1. In this case, L equals 2, and 2 times 2 plus 1 equals 5. An electronic wave function for a hydrogenic system is called an atomic orbital. So, we can represent an atomic orbital by specifying the quantum numbers associated with it. For example, if the quantum numbers n, L, and m are 2, 1, and plus 1, we can represent the atomic orbital by listing the quantum numbers inside the ket symbol, like this. Alternatively, we can just list the quantum numbers as subscripts for the Greek letter psi, like this. Since, among other things, psi provides information about the probability of finding the electron in any specified region around the nucleus, it is customary to refer to an electron as occupying an orbital or being in an orbital. Strictly speaking, it's really just a mathematical function. Orbitals with the same principal quantum number are said to belong to the same shell or level. Orbitals in the same shell with the same L quantum number are said to belong to the same subshell or sublevel. So, we can specify a subshell by stating the values of the quantum numbers n and L. It is more common to use what is known as spectroscopic notation, where a code letter is used instead of the value of L. The code letters are S, P, D, F, and G for L equals 0, 1, 2, 3, and 4, respectively. To refer to a subshell, we write the code letter for L next to the value of n. For example, the 2p subshell refers to all the orbitals for which the quantum numbers n and L are equal to 2 and 1, respectively. Note that we can also use the name of the subshell to refer to any one of the orbitals in that subshell. So, 2p orbital refers to any one of the orbitals in the 2p subshell. Let's take a look at this question. What are the orbitals in the 3D subshell? Pause the video to figure it out, then resume when you're ready to check your answer. Okay, 3D means the quantum number n is 3 and the quantum number L is 2. Remember that the letter D is code for L equals 2. Since L equals 2, the allowed values of quantum number m are -2, -1, 0, +1, and +2. Therefore, there are 5 possible 3D orbitals. All of these have n equals 3 and L equals 2, but they differ in the m quantum number. We can refer to these orbitals as 3D plus 2, 3D plus 1, 3D 0, 3D minus 1, and 3D minus 2. Let's try another question. Which of these two numbers is larger? Choice A, the number of subshells in the third shell, or choice B, the number of orbitals in the second shell. Pause the video to figure it out, then resume when you're ready to check your answer. Let's look at choice A. In general, The number of subshells in a given shell is just equal to the quantum number n. This is because the allowed values of L goes from 0 to n-1. That means there are n possible L values for a given n. So, for the third shell, where n is equal to 3, there are 3 subshells, corresponding to the 3 possible values of L. These subshells are the 3s, 3p, and 3d subshells. What about choice B? In general, the number of orbitals in a given shell can be shown to be equal to n squared. So, for the second shell, there are a total of 4 orbitals. N equals 2, and n squared equals 4. Here's another way to work it out. For a given n, there are n subshells. So, for n equals 2, there are 2 subshells, 2s and 2p. For a given subshell, there are 2l plus 1 orbitals, each one corresponding to an allowed value of quantum number m. For the 2s subshell, L equals 0, 2l plus 1 equals 1. There is only 1 orbital in an s subshell. The quantum number m for an s orbital is 0. For the 2p subshell, L equals 1, 2l plus 1 equals 3. There are 3 orbitals in a p subshell. The quantum numbers for these p orbitals are -1, 0, and +1. So, the total number of 2s and 2p orbitals is 4. The correct answer is B. There are more orbitals in the second shell than there are subshells in the third shell. The allowed energies for the bound states can be shown to be given by this formula. Here, Z is the number of protons in the nucleus. Mu is the reduced mass of the electron and nucleus, which is essentially the mass of the electron. E is the fundamental charge of 1.6 times 10 to the negative 19 coulombs. Epsilon naught is the permittivity of free space. H bar is Planck's constant divided by 2 pi. And n is the principal quantum number. We can simplify this expression by lumping this bunch of constants into just one, r, which turns out to be equal to an empirical constant known as the Rydberg constant. To 3 significant digits, the value of the Rydberg constant is 2.18 times 10 to the negative 18 joules, or 2.18 attojoules, or 13.6 electron volts. Let's apply the formula for the allowed energies to this question. Which of the following has a first excited energy level equal to -r? A. A hydrogen atom. B. A helium ion with a charge of +1. Or C. A helium atom. Pause the video to figure it out, then resume when you're ready to check your answer. Let's see. Recall that for a hydrogenic system, the formula for the allowed energy levels is -r times z squared divided by n squared, where z is the atomic number and quantum number n is restricted to positive integers. This means that, for a given system, the lowest possible energy level corresponds to n equals 1, and the first excited energy level corresponds to n equals 2. For a neutral hydrogen atom, z equals 1. Plugging in 1 for z and 2 for n into the formula gives us a first excited state energy of -r/4. For a helium ion with a +1 charge, z equals 2. Plugging in 2 for z and 2 for n gives us a first excited state energy of -r. So, the correct answer is choice B. How about choice C? For neutral helium atom, z equals 2, but a neutral helium atom has 2 electrons. It is not hydrogenic. The formula we have here is not applicable. We will deal with systems with more than 1 electron in a future lesson. Let's look at another example. In a hydrogen atom, in which of these orbitals would an electron have the highest energy? Choice A, 3s, B, 3p, C, 3d, or D, none of these. Let's see. Recall that for a hydrogenic system, the formula for the allowed energy levels is -r times z squared divided by n squared, where z is the atomic number and quantum number n is restricted to positive integers. For the same z, we can see that the energy depends only on quantum number n. It should be easy to see from the formula that a higher n means a higher energy. If we look at choices A, B, and C, the orbitals given all have the same n. For these orbitals, n equals 3. These orbitals, 3s, 3p, and 3d, are degenerate. They are quantum states with the same energy. Therefore, the correct answer is choice D. In general, for hydrogenic systems, orbitals in the same shell, which have the same quantum number n, are degenerate. In a future lesson, we will see that this is not true if there is more than one electron. The energy associated with atomic orbitals in those cases will depend not just on quantum number n, but also on quantum number L. In the next lessons, we will compare experimental observations to predictions based on orbital energies. Specifically, we will examine absorption and emission spectra, ionization energy, and the effect of magnetic field on spectra. We will also take a closer look at the orbitals. We will learn how they are graphically represented. We will also look at information from the probability density function. Finally, we will learn about electron spin and why it is needed for a complete quantum mechanical description of any atom or molecule.